So, and this will make more sense. I'll draw you a picture similar to what you saw from Sumit of how this is, of what this boils down to. It boils down to something like a tree, and that's where this children word comes from. If the terminology doesn't make sense, don't worry too much about it. Just remember, the things that the sum adds together are called the children. Okay, and so then we could ask, well, what happens if we try to do something more complicated, like u is x plus 4 times y, right? So this u thing is going to be something, right? What is it going to be? What do I find if I find out the type of... Right, there's two choices, basically, right? It should either be a sum or a product. And if you think about how math is nested, right, the pluses are nested around the times, right? If you were to manually add parentheses, it would be nested like this, right? That's why the sum gets to be the outermost version of it. Okay, so that's why sum is the right answer. And then we can dig in and ask, okay, what are the children? Obviously, one child is just this variable x, and the other child is the product of 4 and the variable y. Okay, so that doesn't appear to be totally magic. And then we can, dig in and say, okay, who's my child with index 1? What's that going to be? I heard x, and you're not thinking Python yet, because 1 is the second, right? 0 is the first, 1 is the second, so it's the 4 times y guy. All right. And then we can dig in even further, so we can say u children 1, children 0. What do I get now? 4. There you go. All right. Any questions about this? Nope. All right. Cool. So we can build our own little math expressions, but that's sort of not. Well, actually, hang on. No, right. Okay. That on its own, defining our own expressions is not that amazing. Oh, yes, sir. Question. I can't hear you. Can you speak up? Right. So the question was, SymPy does something similar. Why do we need Pinbolic? Great question. Basically, Pinbolic and SymPy are focused at different tasks. So SymPy is focused on being a good computer algebra system. So when you type in some stuff, it'll go as you hit enter on that the first time, it may go and rewrite this expression behind your back. And if you're wanting to do this with an eye towards code generation, that's not necessarily what you want. You want everything to stay the same. So Pinbolic is a much, much simpler thing than SymPy, right? SymPy knows all about integration and differentiation and stuff. Pinbolic's focus is really more on code generation. If you want to know more, on the web page for Pinbolic, in the FAQ section, I've got a section that tries to make it clear what SymPy is good, in my opinion, anyway. SymPy is good for and Pinbolic is good for. Does that answer your question? Okay. Right. So, next thing that we're going to need to want to do is, once we have our expression written down in this, we're going to want to dig back down into it and modify it somehow, right? And the way that this goes here is, so here's some simple sample expression, whoops, which is like x plus 3 to the 5th power, so that's the power is the outermost thing, then the sum, then x, 3, and the second argument of the power, right? If we want to go and traverse this, we're going to need another object that's called a mapper, which is kind of weird sounding. And the way that this works is that these mapper things have a function in them, right? A mapper is another object. In this case, this derives from some voodoo inside of Pinbolic that has a mapper, that has a function in it called map_sum, map_sum. Can you guess what that's going to do? It's going to get called when inside of this expression we run into a sum. Right? So let me show you how this works. So we make our my mapper here with map_sum, and as soon as we run into a sum, we want to print it. Okay, so here's my u. Was there a question? Sorry, I didn't hear you. Oh, no, okay. Right, so here's my mapper thing with map_sum that prints. Okay, I make a my mapper, and I stick this u thing into there. And not very surprisingly, since there was a sum node inside of there, once I run into it, I print its children, which are variable x and 3. Not rocket science. Now here's a puzzle for you. Here's an expression that has two sum nodes in it, right? There's a plus in here, and then there's a plus back there. So the nesting of this says like this guy here is the outer sum, and then there's the inner sum that's inside of the power, right? If I call my mapper guy on this expression, what's it going to do? The basic question is it going to print one sum or is it going to print two sums? It's only one, right? Because what I haven't done is said, well, once I've run into the sum guy, I also want to do the same thing. Here's a CS word, recursively, if you've heard that, to the same other, to all the other sum nodes that I might run into in the rest of my expression. So, right, this other sum is sort of missing. And what I'm going to do is I'm going to take my mapper guy, and I'm going to drill it open and try and fix that issue. So now this is going to be called mapper2. And, well, what do I want to do? I want to do the same thing to the children of the sum, right? How do I do that? I just make a for loop. For child in expression.children. And then there's a special thing I can call on a mapper called rec for recursion. And I'm going to recurse on each of the children. And now if I feed my new my mapper that same expression, lo and behold, there's two sums like we expected to be. Right? So what have we learned about these mapper things? They have a method, or they have a function in them for every node type, for sums, products, variables, constants, whatever you might run into, that's called map, whatever that thing is. And if we want to, inside of one of these inside of one of these functions, descend even further into the children, then we need to call that guy recursive. Okay. One more thing. So, what do you think? Where do you think this mapper2 guy knew what to do with, say, a power or a variable? Where did that come from? We didn't tell it. So how did it know? Right, it inherits, right? Remember there was this object thing called inheritance. It inherits from this walk mapper, and the behavior that this walk mapper implements is, well, just, descend into all the little details of my expression and, call the next method down, right? So that's where this my mapper knew what to do with powers and all the other stuff. because it inherited that behavior from the walk map. Okay, so that means all the interesting stuff that we're going to run into is going to be a mapper, right? All the interesting operations that we can run are going to take this form of a mapper. So for example, something that we might want to do is print our expressions in a way that's a little less ridiculous than this funny parenthesis loaded stuff up here, right? So let's try and make that happen. And the way that we would make it happen looks a little bit like this. So we'll create a new mapper called myStringifier. Stringify, which means like turn it into a string. It inherits from a recursive mapper, which knows nothing but this recursion mechanism that we talked about. And then we do whatever we need to do to turn each of these expression types into a sum, so into a string, so like a bunch of characters. For example, in order to turn a sum into a string, what we need to do is, well, each of the children of that sum needs to turn itself into a string, and then we join the rest. We join what we get from that with plus. And in Python, that's spelled, open quote plus close quote dot join with all this stuff, right? And here we call rec to see, okay, whatever is in that sum is going to turn itself into a string. So we're going to join all these strings by pluses. Similarly for times, for a variable, really the string representation is just the name, and for a constant, we just let the constant figure it out, right? So if we do that, we define that, and we can call myStringifier. Well, I'll make myself an instance of this guy, and I'll call this Stringifier guy on my U, and I got an error. So the innermost error was myStringifier has no attribute map power, and then we get another message down here that says unsupported expression error, myStringifier cannot handle expressions of type power. Huh. Can you see how to fix that? Right, we just need to tell it how to what to do with a power, so we'll do exactly that. Def map power, self and expression, and how do we do that? What we return is the string version of the base, right? Then we add this power symbol, which is in Python the 2 stars. And then we recurse on the exponent. Okay, let's try that again. And that worked. You have some criticisms about what we wrote there? What's not to like about this? Right, in order to be, actually valid, it would probably need some parentheses, right? And so, as you can probably guess, there's already a thing in Pinbolic, which is in the submodule mapper.stringifier, import Stringify Mapper. Oh my God, so much word. And that is a little bit smarter about how to place parentheses. So specifically, if you want to change how some of this stuff is printed, you would inherit from this Stringify mapper rather than build your own from scratch. Right? So here's what this does for you. You can create expressions that describe your code, right? That describe what you want to do. And then you can modify those expressions in your own ways by deriving your own mapper. Okay, so let's try another mapper thing. So here, perhaps the most popular mapper thing that we might want, or that we might want to derive from, is called an identity mapper, which sounds weird if you think about it at first. So let me show you. From Pinbolic.mapper, import identity mapper. And let me make one of those. And let me grab this expression guy. And I can run my identity mapper on this U thing. And what do you think I got if it's called identity? Oh, no big surprise, exactly the same, except one thing to note is it is equal, but it's not the same. Hang on, I'll expand this out again. That's kind of a subtlety. It's equal, but it's not the same object, right? We got a new object that's actually structurally the same as the old one. It's just in a different location in memory. Okay, all right. But really, the interesting bit is now if we can inherit from this identity mapper guy, which allows us to do any type of rewriting on our expressions that we might want. So I'll go and inherit. I'll call this my identity mapper, which inherits from this identity mapper guy, and say I want to change what this does to sums. Like let's say whenever we run into a sum, we want to multiply that by 2. And that doesn't make a whole lot of sense, but I'll show you in a second, or you'll see in a second a couple more examples that make more sense. So, but let's just say whenever I run into a sum, I want to multiply that by 2. Right? How do I do that? Simple. What should I write? I've got this expr guy, and I want to multiply it by 2. One simple way of doing it is just 2 times expr, right? And then if I do this, well, lo and behold, as you can see, it's gone and multiplied the sum by 2, right? So that way you can change how different parts of your expression get rewritten, right? So when you run into a specific variable and you want to expand that out, you just return, you override an identity mapper and you return something different in that spot, right? That way you can change different parts of your expression pretty simply. Okay. Now, if you think back to our target application, what we're wanting to do is blur images, right? So something that we may want in our funny expressions is a custom operation that Pinbolic doesn't yet know about that could be blur image, right? Okay. So how do we do that? Fortunately, not too hard. And that's in here in the notebook 03, defining custom node types. What we'll do is I'll just make myself an X, and the custom node type that I'll define is called derivative operator. And so this takes maybe an X derivative of something, right? And we have to tell it what it operates on, right? What is it taking a derivative of? And we'll call that the operand. And we'll stick it into an attribute of our object. Then this little bit here is some voodoo that you just have to basically swallow as it is. That's something that Pinbolic needs. It's called _get init args. So this is where you have to tell Pinbolic what arguments were passed to this init guy, right? And since the only thing that we passed is the operand, that's what we return there, and we return that inside of these parentheses with a comma at the end, right? So in here you just list all the things that initially got passed to the init, which was, if you remember, that was called the constructor, right? Okay, and then the other thing that we need to say is when we noodle this derivative operator through a mapper, what method is going to get, or what function is going to get called, and we say that by defining this mapper method thing down here. So we say, okay, mapper method is equals map derivative operator. Right? So when we run into one of those in a mapper, then map derivative operator gets called. Okay, so we go and define this guy, and then we can immediately start writing expressions with that. So we could do x divided by the derivative of whatever this is, right? And if we do that, we get, quotient of x, derivative operator, blah, blah, blah stuff. Okay. Then we could write a mapper that takes all these derivatives and, I don't know, somehow, say, multiplies them by 2. We'll call that the derivative doubler. It inherits from the identity mapper, and how would we make it double all the derivatives? Right, we override this map derivative operator guy. And what does it need to return? Right, 2 times the guy. If we apply it, then if you look, well, our derivative operator now has a 2 times wrapped around it. Okay, so now we can do at least 3 or 4 new things. Thing 1, we know how to take a description of a computation, right, in terms of math expressions, and stick it in a computer. 2, we know how to walk over those expressions. 3, we know how to rewrite them. 4, we know how to stick new operations, like our blurring operations, into those expressions. Those are the 4 things that we've learned just now. Okay, there's a bunch more stuff that comes in the box for Pinbolic. I'll just briefly walk you through that. So for example, if you have an expression like this here, right, x squared plus y squared, you might want to see, well, what does that give me if I plug in values for, say, x and y? And the mapper that does that is called the Evaluationmapper. And I have to supply it with the values for, say, x and y. And then I can call it on my expression, and it goes and evaluates that expression for me. So it computes the value of this guy with those values plugged in. Another thing that you might need is finding the variables that are in your expression. That's called the dependency mapper. And just like that, I know that in my expression I've got x's and y's. Coming closer to our actual goal, maybe I want to take this expression and turn it into C code or Python code or something. Yes, sir? Recap the steps to okay, right. So how did we get here? Step 1 was we started with the stuff that Pinbolic apparently knows about, right? We started with variables, and we're able to add them together and build big, complicated, nested data structures. Well, in this case, not so big and not so complicated, right? Like this x plus 5, which turns into sum with children variable and 5, right? So we can build data structures that describe some math. Next, we worried about how do we process, how do we change, how do we work with these expressions once we have data structures of them, right? And since it's big, complicated, and nested, the only way to really break it down and to have to think about it concisely is is to see what happens at each individual part of the expression, right? So say, what happens if I run into a sum? What happens if I run into a variable? And I do this by making a mapper and ideally deriving it from one that's already there and telling it, well, now my friend, if you run into a sum, do this here, right? So for example, again, if we want to say every time that we run into a sum, we want to multiply this by 2. This is literally what we do. You run into a sum, and what we turn the sum into is 2 times that sum. Okay. Then, the next thing we wanted to do was stick our own custom stuff, like the blur operation that we'll need, into the expression tree. And we do that by inheriting from pinbolic.expression, which is the base class for all those things. And say our derivative guy is going to need something that it takes the derivative of. So we were going to need that. There's the getInitArgs voodoo. This is how this couples to the mapper end of things. So if we then run a mapper on an expression that contains a derivative operator, the mapper will know, oh, we need to go into map derivative operator. OK, and then we can make ourselves a data structure, an expression data structure that contains one of these guys, a derivative operator, and run our own rewriting on it. So it's gotten rid of it for me, but you might remember I just inherited from identity mapper and overrode the map derivative operator to multiply that by 2. OK, right? So 4 things. Expressions, walking through expressions with the help of mappers, modifying expressions by overwriting and returning new things from those mappers, and lastly, defining your own custom stuff that goes into those. Any questions so far? Nope, all good? All right, cool. So, right, we were talking about things that already come in the box. So I showed you that you can find, the value of an expression, right? So if you have a formula like this, you might want to know, what does it give me if I plug in values? That's the job of the evaluation mapper. Another thing that you might want is knowing the variables, dependency mapper. Another thing that you might want is that formula that we have here, maybe x plus 4 to the 17. We might need that turned into some code, right? Apparently, there's something called a C code mapper. You can take a wild guess what that's going to do. It's going to turn it into some C code, right? So, and maybe you can already see how the circle is going to close itself, right? We're going to describe our stupid calculation somehow, and then some derived version of the C code mapper is going to turn that back into C code for us. And we're then going to go and execute that, and hopefully that'll give us something fast. Right, OK. Let's see that, yeah. OK. 2 things that I don't really want to go into the details, but if you're curious, I'll point at the notebooks that show you how to do that. Obviously, Pinbolic and Simp are relatively similar, right? Just with different purposes, but the 2 talk to each other, right? So if you want to do some calculus, and then based on the result of that calculus generate some code, then there's a way to get the output of SimPy into Pinbolic, or the output of Pinbolic into SimPy. So you can very easily go both ways. Right. And just for entertainment and maybe to make the whole business a little bit clearer, so here's a relatively complicated looking expression. Right? I made a u, which is x plus 4 to the 3, and I made an h. And then this thing here comes out to x plus 4 to the 3 plus 2 times blah, blah, blah. I'm not going to read it all out. The actual data structure that represents this, we can see. Hang on, I'm going to use the uncleared version of this just because it's easier. Let me show you that. Let me make that a tiny bit smaller. The data structure that represents this looks like that, right? So the top level guy is a sum, then from there dangles a product of h and 2 and some sort of power thing that has as a base a sum and as the exponent a 3, and then that's also a child that happens to also be a child in the original sum, and in the original sum there's also a 4 times this power h to the second power guy, right? So that's how it ends up being represented inside of the computer, right? Okay, all right. Scroll where? So this, if you want to see how this is done, the notebook that does this is the notebook number 7 in section number 2 is called internal representation. Right, okay. So then the objective was, let's see if we can apply this so that it can generate some fast code for us. So let's see if we can make that happen. And the tool that makes this happen for us is called Loopy, at least in this setting. What does it do? It talks to this thing that I mentioned called OpenCL that we can throw some C code and it executes that for us. And you'll see a little bit more about OpenCL tomorrow, like I said. So what does it look like? Hang on, I'll go back to the cleared version just to make it a little bit more entertaining. So we import a bunch of stuff, which doesn't really matter too much. This here, if this looks a lot like NumPy, then that's not a coincidence, right? We make 2 arrays A and B full of n random numbers that have some sort of data type, in this case single precision floating point. And then what do we want to do with this? Based on this description, can you guess what this is supposed to do? Right, and what's that function supposed to do? So there's A, there's B, and there's Cij. Right, so if you remember your linear algebra, then that might look like an outer product of 2 vectors. Right, so you have like one vector here, 0, 2, 5, 7, something, and another vector here, I don't know, 1, 2, 3. And there's 2 ways to multiply those together. One is the dot product, which just gives you one number, and which is also called the inner product. Or there's the outer product, which gives you a matrix, and this entry of the matrix is 1 times 0. This entry of the matrix is 1 times 2, and so on, right? And so what this guy here does is it gives us the outer product, which is a formula, looks like Cij equals Ai times Bj, right? So, and you can by now probably guess that, hang on. When I pick this apart, so in this thing, which Loopy apparently calls a kernel, if I look at the first instruction, this guy is an instruction. If I look at the expression, what am I going to get? A Pinbolic expression that does product of subscript on variable with variable I, subscript on variable B with variable J. Right? So that's how this connects back to Pinbolic. This is so if you have a Pinbolic expression, you can stick it right into Loopy, and it'll then hopefully at some point turn it into code for you. Right? Okay. So that's the second part that we've talked about, the Cij equal AI Bj. Can you tell me what your reading of this first line here is? So that looks a little bit like a set written down in math notation, right? The way that it writes out is apparently it's a set of all tuples of integers ij, such that what is true? Right, you get it, right? I is greater or equal 0 and less than n, and j is greater or equal 0 and less than n. Right. So what we've done is said, hey, Loopy dude, please execute this on all these values of I and j. Right? Okay. So let's see if we can convince it to do that. 15 minutes. Okay. All right. Right. So what we're going to do, is we're going to just run our kernel, right? There's this kernel thing up here that we got. Oh, sorry, I could have just used that guy up there. Sorry. Never mind. Right, so what we're going to do is we're going to take our kernel, this thing here, and we're going to set an option on it. This here up here says set option. Set options, and what option are we setting? We're setting the options right CL, and that's just because we're curious. We want to know what code got generated in order to execute this, right? So, and the execution thing is what we're going to do in the next step. We're calling the kernel with arguments A and arguments B, which, if you remember, those were the two arrays full of random numbers, right? And lo and behold, what we got was something that looks suspiciously like some C code that does exactly what we want, right? So we've told it, okay, we want I and j to vary between 0 and n. And so it wrote a for loop in C where j varies between 0 and n, where I varies between 0 and n, and where it carries out our operation, right? Okay, so that was simple enough, right? And if we run this, this might even run reasonably fast. But then the promise that we started with was that the thing that Loopy is going to help us do is rewrite this so that it maps better onto a machine than to just two sequential for loops. And like the things that we need to are going to need to take into account there are going to be, we're probably going to want to parallelize this across a bunch of multiple cores. We might want to vectorize this across a bunch of SIMD lanes. If you've never heard that word, forget that it exists. I'll tell you more about it tomorrow. And we might want to rearrange how the data looks in order for it all to go a little faster, right? So let's try and see what we can do in that direction. So here's one very simple example. Oops, that's kind of garbled. Let me try and fix that. One very simple operation that on its own doesn't do a whole lot is let's take the I loop here, and let's split it into little groups of 4. Okay? Right? So we start from our original kernel guy, and we split the I loop into groups of 4. And if we do that, hang on, let me if we do that, then all of a sudden, this is what we get. So that code already looks less appealing and less like, oh, I really want to write that by hand, right? What's happened here? Well, the J loop is unmodified, but for the I loop, apparently now we have 2 loop indices, I outer and I inner. And then at the very inner bit of it, we've got a check that asks, well, combining my outer and my inner index, have we run over our overall loop limit of n, right? And then there's the actual thing that we want to carry out, which is C is A times B, but it all looks a little less intelligible already, right? And that's the service that Loopy provides. It does all this rewriting for you, and it has less of a chance of making a mistake than if you were to do this by hand. Okay, now why would you want to necessarily split a loop into 4s? Well, something that you might want to do is unroll that loop. How many of you have heard of the word unrolling? Okay, all 3 of you. So let me show you what that means. Here, what has happened, so what have I done? I've split my I loop into little groups of 4, and I've told Loopy, take the inner part of I and unroll it. Don't worry too much exactly about what the syntax is. And what has happened is I still have my I outer loop, but my I inner loop has disappeared. And it's disappeared into just four copies of my code that are just pasted end to end, right? Can you imagine why that might be faster? Exactly, right? So it's actually less code because there's no code for the I inner for loop, which means the computer doesn't have to go check every time that, am I at the end of my loop, right? Obviously, this is only valid if my number n was divisible by 4 to start with. And if you look up here, I actually told Loopy to assume that. Right? That's this guy up here, where, let's see, let me make that a little bigger so you can see it. I said, assume n mod 4 equals 0, right? So if just for illustration, if I go and remove that, then I'm not likely to gain anything, because all of a sudden, in front of every one of the executed statements, I'm back to having to check, have I overrun, have I overrun, have I overrun, right? Okay, so that's one example. Another example that we'll run into in a little bit more detail tomorrow is we might want to parallelize this across, say, some sort of cores, right? And we then end up saying, you know what? Let's make it super simple like that. And when we do that, when we decide let's parallelize this over a bunch of different cores, then we need to tell each core of the computer how much work it's going to need to do, right? And how have I done this here? I've said, take my loop over i's and split it into little groups of 16, and take the outer part of that loop and make it the number of the core. And that there's a slight lie in there, because that, by taking a loop that could be arbitrarily long, could be 200, 5,000, whatever, And making groups of 16, I might end up with, I might just have said, well, take that part of the loop and put it on the 400th core. If my computer doesn't have 400 cores, that's bad, but it's not actually a huge problem, because then I'll just tell however many cores I've got. So you guys do the first 4, then the next 4, then the next 4, and so on, right? So having too much parallelism is never a problem. Having too little parallelism is always a problem, right? Okay, so, and just by splitting loops, I can already do a fair amount of stuff in terms of getting performance. Then there's a bunch of other stuff I can do. So I could, for example, ask Loopy to maybe go and grab the data in A and grab the data in B before the loop. This is back. Hang on. This is back to the sequential version. So I could ask it to grab the B before the inner for loop, so I don't have to read B every time inside of the inner loop. Mm-hmm. Right. No. So this is an example of a kernel where there's just one expression, because we only want to do one thing. But you can have multiple instructions in a kernel very easily. This is just a simple example. Right. And then similarly, I can do something similar in terms of prefetching for the multi-core version. Right. Okay. So let's see. How much time do I have? 5 minutes. Okay. So that's running a little short. So let's connect back to the task that we set ourselves, which was making, it's a little bit funny, but making cats blurry, right? Okay, so how's this all gonna work together? Well, we're gonna do this by describing our operation, right? So the simplest thing that we have here is just, if it's still around over here, this blurring operation. If you remember it from the very beginning, right? All right, and so what we'll do is we'll create a Pinbolic node to represent our neighbor average, right? And this is just the same as you saw. It has a child, which is going to be the image that we want to blur, right? And the mapper method that we couple to is going to be called map neighbor average. Not a huge mystery. Okay, and the image filter that we start with is just very simple. At first, just apply the neighbor average, don't do anything else. And later on, we'll, hopefully in 5 minutes, I'll show you what a slightly more complicated version is. Okay, right. So now what we want to do is turn this into code, right? And, well, how do we turn this into code? The way that we turn this into code, obviously, is we have to break it down in terms of this weighted average of a bunch of pixels, right? So we do this with the help of a mapper. Big surprise. And this is the mapper that takes our averaging operation and breaks it down so that Loopy can understand it, right? So when in an expression we run into a neighbor average, and that's not good because it wraps the word. When we run into a neighbor average, we're going to execute this bit of code here, right? And what is that going to be? That's going to be 2 times the variable, which is just a different name for the that we've assigned here for the child of the neighbor average, right? We're going to take 2 times that variable indexed with II and JJ, which I've cleverly declared up here as just being I plus 1 and j plus 1, just so I avoid writing a ton of index arithmetic. Then add II plus 1, that's the pixel 1 going 1 to the right. Then II minus 1, that's the pixel to the left. II and JJ plus 1, that's the pixel down, and so on, right? And divide by 6. So whenever we run into a neighbor average, we actually go and replace it by that. And similarly, when we just run into a variable, we need to add the indices to it just so that Loopy knows what to do. Okay? So this is going to be the thing. Oops. This is going to be the thing that turns our image processing operation into code. So we take our image filter and run this index mapper on it, and it's given me already a considerably less readable version of what I want it to do to this image. And with that, we're basically ready to feed this into Loopy. So we go and import Loopy. And what we do here is tell Loopy, we want you to perform basically one assignment, namely from to a result variable, which I've declared up here. Result variable is a Pinbolic variable result. And so result variable at II and JJ is this code that we just generated, right? This is what I just made up here. Index mapper of image filter. We paste that into the right-hand side of the expression, right? That's the thing that we wanted to assign to the result. And then the loop domain is no different from what we saw earlier, right? So it's the set of ij between 0 and n. No different than earlier. And I have to actually tell it what the shape of my result variable is. That's a detail that doesn't matter too terribly much right this second. If once I do that, I get Loopy's description of what it has figured out. I've just asked it to do. So it's figured out that I have two arguments, namely three arguments, u, result, and n, which n is the size in pixels of the image. There's the loop domain, which it has broken down as ij, I greater 0, and j greater blah blah blah. You can see it. And the instruction with our generated code, right? Okay. Now let's move towards executing that. And I'll just reread that same cat picture again. And I'll run the Loopy kernel, which the simple generated C code now looks like that. And if I go and plot the result, then I see, okay, it's gotten slightly blurry. I can run it a couple more times. And the result, yet again, is one very blurry kitty. So just at a basic level, this does the same thing as our original NumPy operation, right? And then we can go and start applying transformations to this, right? To make it actually go faster. And here's one example transformation that I came up with. So what I've done is split the loop over I into groups over 16 to parallelize over cores. And I've split my J loop into little groups of 8 and mapped the inner loop that I get that way onto the vector lanes. I've told Loopy how to order the remaining loops, and I can go and execute this. The code already starts looking a little more messy. But now the real judgment is, have we been able to gain some execution time over just plain old NumPy, right? So let's time the execution of this. This code should look familiar, right? This is the thing that we started with. And what I do is I just run a couple of rounds on an image. I think this number of rounds is, whoops, not sure what I just did. This number of rounds is something like 4, and the image that I'm running on, just to make it count, is a 5,000 by 5,000 image, just so that we can actually see some performance differences here. And so the NumPy code, to do 4 rounds of that, takes 0.32 seconds, right? And if I do the same and time the generated version, it's actually a healthy bit faster, right? And now to come back to the last aspect of this, where I said, well, the thing that you should really do is when you go after performance, is you should try and be a little bit scientific about it, right? So obviously this factor of whatever 5 or something that we just got is nice, but how much more do we have a right to ask for, right? Like so, you know, there's this scenario where you could keep doing this, and at some point you run into a brick wall because there's no more to be had, right? And you, in order to be able to tell when you can safely stop, it's useful to think about, well, how much can I hope to extract from the machine, right? So what do you think is the limiting factor here? And there's basically always only two limiting factors to performance. It's either memory access or floating point, right? As in doing actual math. Which of the two do you think it is here? Who's for memory? Who thinks it's the math? I have bad news for you. It's almost always the memory. Doing math has become so cheap. I'll show you more about this in the talk tomorrow, why that's the case. But it's almost always the memory. So let's try and understand how much memory we're accessing. So what I've done here is put together just a little bit of counting. So how many pixels are we accessing? Well, we're accessing, you know, the up guy, the down guy, the left guy, the right guy, and the guy in the middle. That's 5, and we're writing out. So that's 6 total. Times that number. Actually, that should probably just be an n. Now that I think about it. Not that it makes too much of a difference in the grand scheme of things. Then each pixel is represented by a single precision floating point number. So that's 4 bytes. So the number of bytes accessed is the number of pixels accessed times 4. And then the number that's really interesting, because you can compare it to something that is attached to the CPU or GPU that you're running on, is the number of gigabytes per second, right? How many gigabytes were we transferring per second while we were executing our image blur? In this case, it was 9.05 gigabytes per second. And if you then go and look into the data sheet for the processor that I'm running this on, it says about 20 gigabytes per second is what it does at most. So we're doing pretty good. So at best, you know, we might be able to get another factor of 2, but that's going to be about it, right? And so we would have to, you know, fiddle a couple more knobs, rewrite the code a couple more times with the help of Loopy. We would probably be able to get there. But with another factor of 2, we're basically done. Now, the actually interesting thing, if you want more performance than that, would be to try and talk to something that's not a wimpy laptop CPU. But there are these other machines that I'll talk to you about tomorrow called GPUs, where this number, right, I said just the peak thing that this thing can do is about 20. The peak memory, the peak gigabytes per second you can get out of a GPU is more like 500, which means like something like this could go a whole lot faster, right? And with Loopy, you're in good shape to also take your code to those machines, although the code is going to look a good bit different than the code that runs fast on a CPU, right? So as a final thing, obviously it's nice to get performance, but it's also nice to be able to go and change what your code does. So a different image filter is something called an unsharp mask. And it's actually this thing here. So, and that's the I know we're out of time, so I'll let you go in just 1 second. What is an unsharp mask? Well, if you think, what does a blurring operation do? A blurring operation just like washes out the image of right? And the idea behind an unsharp mask is, well, we think about what difference have we applied to our pixel by doing the blurring, right? And if we wanted to, instead of blur, sharpen, why don't we just go in the exact opposite direction that the blur would have gone in, right? So, and in terms of our little image processing language, that's okay. Compute the difference that the blurring would have applied. So u var, the image value minus, hang on. Right, well, it made sense in my head when I wrote it. This back here, from here to here, computes how much I would have moved the value of the pixel by applying the blurring, and then we're going to apply that difference, but in the exact opposite direction, right? So that's what this here does, and all of our fun performance work just transfers over directly, so I can just go and noodle this through loopy. And instead of a blurring operation, this should now go and actually sharpen the image. So let's see. That's close to the original image. Let me run the sharpening a couple more times. That may already have been too many. Well, that's almost there. Well, nah. Let me re-grab the original image and run the sharpening not quite as many times. There you go. So that's the same cat image. You can't quite tell on the projectors. It's clear on my display right there, or on your notebooks. So that's my message to you this morning, halfway morning. What this set of tools that we've talked about hopes to try and help you do, is A, to get good performance across a broad variety of machines, and B, keep your code at least sort of reasonably tidy and flexible so that you can do lots of different operations while saving the same kind of hard work that you've put in to make it go fast on all those bizarre machines. That's all I've got to say. Thank you very much for your attention. And if you've got questions, I'd be happy to take them. Otherwise, we should probably go to lunch. Any questions, guys?
Okay, if there's no questions, lunch is ready, and we'll be reconvening in an hour.
And feel free to come. Sorry, go ahead.
Yeah, go ahead.
If you've got questions, feel free to come chat with me. I'll be around for the whole rest of the conference. Also, see you tomorrow.
Yeah, we'll be reconvening at 2.